Was there only one critical point?
Yep.
So it's 10-6?
5 seconds.
Or whatever?
Negative 5 seconds.
Well, depends on which version of the quiz you had.
But it was one, right?
There's only one.
Okay.
There can only one.
So I'm just wondering how the graph will look like. So there's one critical point for a second derivative. Would that mean at the 0 points it'll do like a little weird thing? Or like, well, like, say you had like 3 critical points in the first derivative. It's like negative, positive, negative. But say the negative and positive was behind the concavity, so like there's like a weird little shape. Like would it zero out, but then keep going down and keep.
I don't know what you're saying. I'm sorry. So yeah, I mean,
So say it's increasing.
Go for the concavity.
Yeah, and both of the decreasing and increasing is behind inflection point. So like, would it decrease and like flatten out and decrease again until it hits the inflection point and then concave back up?
If there was 2 decreasings?
well, inflection point doesn't have anything to do with whether it's increasing or decreasing.
No, I know it has a concavity.
So.
Are you asking if the inflection point will be behind the 2? Like if it's like, say, like one of those cube root functions where it just goes down like that, then there's the inflection point?
Yeah, and say it changes, like it goes for the increase and decrease, it goes negative to positive. Like, how would it work?
Like, how would you draw the graph? If it was like negative and then negative again, so you would have to concave down.
So help me out. So
there's a critical number between 2 concaves downs, so it's just down, down.
So it's just concave down, but
there's
there's 2 critical numbers where it's concave down.
Yeah.
One critical number, yeah.
How would you draw the graph if it was concave down?
So let's be even more specific. There's 2 local extrema, not just critical numbers. Or maybe, or you mean just critical numbers? So
there's there's no local max or local, well, there's one local min, but there's a critical number.
So there could be a critical number there.
Yeah.
And then keep going down.
Yeah, and then there's a critical number somewhere else, but it's
fake.
It's
one of the
also-
fake numbers. That's a 0.
for the first derivative.
So if you take a tangent, yeah.
So it looks like it's going to turn, but it doesn't.
Yeah.
So
Yeah.
we just
How weird things can happen. Normally, at that point, it would have to change concavity, sort of, to kind of do that for a second, right? Let's see. Let me think. I mean, this guy is concave down and concave up. So normally, you would think it has a change. Off the top of my head, I can't. When you get weird functions doing stuff like, this here, and then it stays concave down. We get a little cusp there, right? That doesn't really capture what you're asking though, right? And then I can have it, I can, whoa. I can stay concave down forever and have multiple critical numbers. This is where the first derivative would be undefined, right?
Mm-hmm.
So those would be critical numbers. They are local mins, every single one of those, but it's concave down everywhere, right? So that could happen. I don't know if that's quite your situation you're talking about. Is it? Not really quite. Yes?
Because aren't there situations where it can be concave down twice, but it's still differentiable? Like, would that just mean that it gets less negative and then it...
Concave down twice.
So like, let's say you have like 2 critical numbers next to each other and both of them were concave down.
Alright, so you have a situation where the first derivative is 0 at 2 places.
Yeah. And they were both concave down.
But it's concave down across this whole interval. That's what you're saying.
Well, yeah, like how would you draw that?
2 places where it's both concave down.
Yeah.
So it's concave down at A and B.
And B.
So it's concave down across this whole thing, is what you're saying. Because it matters. I mean, if it's... Alright, how do I want to say this? So... I almost understand what you're trying to say, but I mean, if it's concave down across this whole thing, is that what you're saying? Because that's a different thing than what it could be. I don't know.
Because would it just keep like, would it just kind of look like that? Or
so you can't be concave down at a point. Yeah, you're concave down across an interval of points, right?
Okay.
Does that make sense?
So like, let's say it was like from A to B and then B to C. It was concave down.
But it's like 0 at B or something?
Mm-hmm. So would it like stop at B and then keep going down? And then go, like, how would that work?
All right, so without the context of an actual function, it's hard to tell what is allowed to happen and what can't happen. Does that make sense? I mean, if I just threw this at you without the context of a function behind it, I could actually give you a situation that would almost be impossible to happen. And then it's like, how the hell do I draw an impossible situation? So you have functions where really weird things happen. I don't necessarily have like a bank in my head of what could possibly happen, what can't possibly happen. I just attack functions as they come at me, right? I'm not sure where this come from. Is this coming from somewhere, or is this just something that you thought about?
Homework.
Where in the homework does it say that?
Well, no, it just, I had situations where it was like concave down again, and I just kept getting the sketch wrong.
Alright, so you certainly can have a place where you have a critical number for the second derivative, but it's negative,
Yeah.
right? Sure. So it's concave down, still concave down.
Yeah, like how would you sketch that? That's what I'm trying to say.
Alright. Something like, how do I want to say this? Well, let's look, like this here. What's the first derivative?
4x is the third.
And what's the second derivative?
So,
What's the critical number for the second derivative? 0. Plug in a negative, you get positive. Plug in a positive, you get positive. So it's sort of like that, just the reverse, right? If I would have put a negative on here, then it would have been exactly what you said. And let's go ahead and make it exactly what you said. Now here's the thing. Second derivatives being tricky are even more tricky. Because we know what x to the fourth looks like, don't we? It looks like a steeper and a flatter at the bottom, but not like crazy flat, but right, it's flatter and steeper than a lower degree parabola, right? Mm-hmm. So there's nothing here that tells me, I mean, isn't it, now of course I changed it to negative, so it would be down, right? But still the same idea. So it's concave down, and then it looks like it's going to change concavity, and then it doesn't change concavity, and that's horrible, Jeff, but we'll live with it. So is there anything, can you just look at that and tell, without doing the math, that this is actually a critical number of the second derivative? No. Do you see what I'm trying to say? Second derivative critical numbers are not easy to find on the original function's graph. This is actually, I like this question now. Sorry, it took me a while to get around to it. But this is a good illustration of the second derivative is kind of delving deeper into the function's shape. So looking at this, if I just gave you this graph and I said, is that a critical number of the second derivative? I would hope people would say no, when we're actually wrong. But that doesn't mean we don't know math. It just means we need the math to tell us that there's something weird going on there. I don't know if you guys are with me here. Second derivative is a little too far removed from the original function to tell real good details. Now the first derivative is only removed once. So I know that that's going to be a critical, and in fact I know here, I know that that's going to be a critical number of the first derivative, right? Definitely. And obviously this is way obvious that it's a critical number of the second derivative because it's concave and then it's concave. But that is nowhere near obvious that it's a critical number of the second derivative. I just can't see it. And we're not supposed to be able to see it, really. Does that make sense? The second derivative is a little too far removed from the original function to be able to see everything that it would tell me. I don't know if you're with me here. Do you agree with me? There's no way. If I just gave you this picture, you would not say that that's a critical number of the second derivative.
No.
You wouldn't say it.
I wouldn't.
And we would be wrong. And I wouldn't say that either. I know enough to say I don't know. But if I'm a student, I'm like, no, it's not. It doesn't look like it's the first derivative, yeah, but the second derivative, no. I'd be wrong, but it's fine, because we're not supposed to be able to tell. So your question was sort of the reverse. How would I draw it if that happened? It actually wouldn't look, look, there, it sort of happened. And it doesn't really capture that. So how do you draw concavity 0? You don't, really. Right? And what's really neat is, I mean, do you guys know what it looks like when it gets to here? Do you guys know what that looks like? It's a really cool thing to do in your graphic calculator.
Is it a parabola?
It's still a parabola, but So think about it. When I square something less than 1, it gets smaller. So when I raise 0.9 to the 100th power, somebody help me out. What's 0.9 to the 100th power? Let's see if your calculator can even handle that.
2.65
times 10 to the negative
5.
All right. Damn small as hell, right? So here's scale of 1. 0.9 is times 10 is like here. So here's the cool thing. If you actually graph this, does anybody graph this? Doesn't it look like this, basically?
Yeah.
Because the curve is so far, it curves really fast right there. And the second derivative is it's going to be to the 98th power, right? Take two derivatives. So the curvature at a given point is going to be 100 times 99 times x to the 98th, right? So the curvature, well, I don't want to get too into it, but, and I'm not sure how this relates to anything, but it's the fact that the curve, that the concavity is 0 at 0 actually has a little bit to do with the fact that it's so flat there, but not perfectly, right? I mean, it's not a straight line here, is it? It's just so damn small that it looks like a straight line when you first graph it in a graphic calculator. It just gets there really fast. So, I mean, there's aspects of the function that the math tells me about that I could never get from it just looking at it, right? Which I love, because then I say, hey, look at that. There's one of a billion reasons why math exists. Hey. So we can see things that we could never see just looking at it.
So how would you know it's supposed to look like that? For having...
Well, I did it by just figuring out if I plugged a 0.9 in there, what would it look like?
Yeah, but I mean, say we did do the second derivative, and it would be what? 100 times 99 x, and it'll still be 0.
So say that it looks like, now if you just gave me this picture, you're not wrong. It's just your scale on some scale, this looks like this. That scale would have to be like really
infinitely small.
Really, really tiny scale to see that, but still, you wouldn't be wrong. So the work we're doing is still not strong enough to identify how quickly that curve is changing, right? Do you guys get what I'm saying? Which translates into how flat it looks from a normal perspective, right? If you graph it by hand, I hope it looks like that. If you turned in this, I'm like, oh, they just copied it out of the calculator. Right? What you graph should match your work. Okay. And we're still human. We're not going to be perfect, which is fine, which is awesome. So we're not wrong. It's just not perfect. That is the correct curvature of that, the idea of it, but it's just more severe than we would think at first. Okay, that's enough of that. Yes.
Could I ask you something for 4.4?
No. Yes.
Can you just explain a little bit the indeterminate powers?
Oh, that last part. Okay, good. All right.
Like number 4.
Gotcha.
Yeah.
Well, it's kind of just generally indeterminate powers.
Yeah. So this is at the, like on page 306, they have an example of something raised to a power. So, I mean, this has been indeterminate forever. When I first teach my students that anything to the 0 power is 1, I say 0 screws us up all the time, let's not worry about that. But now we're at the point where we have to worry about it. So 0 to any power is 0. Anything to the 0 power is 1. So indeterminate forms are forms that are competing with each other, right? So I had a really good question. Somebody came by and said, is this an indeterminate form? Is that an indeterminate form? Something over 0 is infinity, right? Infinity over something is infinity. They're not warring with each other. They're agreeing with each other. That's totally determinate. It's like really infinite, right? The top gets really big, the bottom gets really small. It's like infinity.
The infinite.
Sunday. So, but this is competing with each other. That's 0, that's 1. Oh, what the hell's that then? Can't be both. So it's got to be whichever one's going to its respective 0 quicker. So somehow L'Hopital should come into this. And then the other ones, they say infinity to the 0 power. That should kind of make sense, maybe. Anything to the 0 is 1. Infinity to the anything is infinity. So infinity to the 0. The hell, right? And then, what else? Oh yeah, this is the one that seems kind of counterintuitive, but that actually is an indeterminate form. Believe it or not. Because it's like this. That one.
Do you take the ln?
That's your famous. Hey, we've seen this kind of thing before. We had to do implicit differentiation.
Yeah, so it would be 0 times ln times the e to, so it would be 1 times 0, which would be 0.
So all of those are indeterminate?
Yeah, all of these are indeterminate forms that you can do what we're about to do. And this should be very familiar. This is why I didn't really say too much about it, because it's exactly what we had to do before. So I say, if I want this limit, I say that this is y. So what I want is the limit, as x goes to infinity, of
use implicit.
y. No. We do the same first step. Let me go through this example with you, because this is the famous one. It's famous. You guys with me so far? I mean, I really didn't do anything, did I? Yay, Jeff. You did nothing. So what I do is I take natural logs of both sides, like somebody said. That's what we did before. When I had something that was in a form I couldn't differentiate, I did natural logs and then did implicit differentiation. Here I'm not differentiating. I want to get the limit. So the minute I take a natural log, what can I do?
You can bring down the x.
Good. The x comes down.
And then you can
Now, let's focus on this. Does L'Hopital like that? And what form is it in now? So it was, what form was it in to begin with? Let me stop there. This right here, the original problem, what form is that in? What indeterminate form is that in? As x goes to infinity, this goes to? No. This goes to 0, this goes to 1. As x goes to infinity, that goes to? Now, you guys are like, Jeff, listen to me, Jeff, listen. That's 1, dude. Do you understand? Did you realize that, Jeff? The reason it's not 1 is because only 1 raised to any power is 1. Is this actually ever equal to 1?
No.
That's the problem. So it's never actually equal to 1. But if it's going to 1 faster, then that's going to infinity, then it's going to kind of either be 1 or something close to 1. It's going to agree somewhere. If that's going to infinity faster than that's going on, then maybe the limit is infinity. So it's all about which one's going to its respective limit quicker. Do you guys understand why? This is the form it's in. It never actually attains this form, right?
Yeah.
It's like Super Saiyan 7. Yes?
Wouldn't it be, because if you plug in the infinity, wouldn't you just get 0 to infinity?
No, because it's 1 plus 1 over x. So it's 1 plus 0.
1 to the infinity?
No, so yeah, 1 to the infinity.
Oh, okay.
Exactly. I really hope you understand. This is never 1. So if you did 1.0000001 to the 80 trillion, believe it or not, that's going to be a big number. It's going to be huge. Right? I don't think your calculator can handle it. You could do something like, do this for me. What's 1.00001? 4 zeros. Let's see if your calculator can do to the 80th power. Somebody help me out. Let's see if it can do that.
It's 1.008031682.
All right. So then if you do the 800 power, can it handle that?
I got 1.083.
1.08,
Yeah.
right? And then 8,000?
So it's going to go up, so it's going to be 1.83.
And then if you did 80,000, you can see how it's going to keep going, and that would be going to infinity, right? If I only allowed the power to grow and I kept the inside just above 1, that's going to go to infinity. If I kept the inside at 1, and then it doesn't matter what power I put on, it's going to be 1. So they're at odds with each other. This inside wants it to go to 1, the outside wants it to go to infinity. L'Hopitals can see who wins that race, right? But, so is everybody kind of with the idea behind it? The reason we do what we do is the exact same reason we did it when we were trying to take derivatives, because I didn't have a rule for what to do here. I don't have a rule for what to do with this form, but I do have L'Hopital's rule. So I want to put it in the form that L'Hopital's can handle. So is it in that form yet?
Yeah.
What form is it in now?
0 times infinity.
Okay, so infinity times 0. Is that a form L'Hopital's can handle?
No.
Not directly, no.
So when you take the derivative, it's going to be 1 over, so infinity over...
I'm not taking a derivative. We can't do that yet.
Yeah.
Because again, like we just said, it's not a form that L'Hopital's can handle.
So would it be ln of 1 plus 1 over x divided by x?
No, you can't just take the x down. It's got to be the same expression.
Ln of x?
No, you can't bring an ln out of nowhere. X is multiplying by x. It's the same thing as dividing by
1 over x?
Good. You got to be used to writing. That is the exact same expression as that. They are the exact same. Why do we normally not do this? Because normally this is stupid. Right? This is like, what the hell? So I got 2x and somebody goes, I like to write that like that. Who are you? So, but I want you to realize, now it is remarkably smart to do that because L'Hopital's can only work when it's a ratio, right? L'Hopital's only works when it's a ratio. So now, that's a true fact. I would never have done it before this, because that's just like, what the hell is up with you? But now it's like, oh, okay, now I see the utility of the fact that that is true. That's nice that it's true, so I can do this. Now, real quick, also, you got L'Hopital's and you got quotient rule, right? This is not quotient rule, just to head that off. L'Hopital's, the definition says that the limit of this function to this function is the same as the limit of the derivative of this function to the derivative of that function. It's not a derivative rule. It is a rule about limits. So I'm not breaking any rules. I'm not taking the derivative of this whole thing. I'm taking the ratio of the derivatives. Right? Do you guys understand where I want you to be careful? Don't suddenly go, well, now I can do everything top and bottom separate. Yay, Jeff. No. All right, if I ask you to take that guy's derivative, well, hopefully you bring that back up, but you can use quotient rule there, right? All right. So how does L'Hopital's work now? Yeah. Because now it's in the form, it was infinity times 0, now it's 0 over 0, right? Maybe. And so now what's the derivative of the top?
1 over 1 plus 1 over x.
Good.
Times 1 negative 1 over x squared.
Okay.
And then
I think we did this one, didn't I?
1 over x squared.
So that limit is 1. But I got the answer for the limit of ln of y. How do I get the answer for the limit of y? I just have to. How do I kill ln? E. So this is the famous place where E comes from. That's where E comes from.
He was born between infinity and 0.
That's right. That's a really cool opening to something. Samurai Jack's brother. Or Samurai Jack. Where was he born? Somewhere between 0 and 50. Thank you. So you guys, so that's a weird thing, but it feels a lot like what we did with implicit. We're not differentiating. We're not doing like implicit differentiation directly. We're doing L'Hopital's, which uses derivatives to figure out limits.
So did you ever take the limit? Because you carried the limit all the way.
Oh, right here. The limit is x goes to infinity. If 1 over x is 0, that's why this became 1.
Okay.
So right there I applied the limit because now it's not indeterminate anymore. If it would have still been indeterminate, I would have done L'Hopital's again until I get it beaten down into
So
submission.
you can apply L'Hopital's rule.
Totally, because every time you take a derivative, that is its own function, and if any function is a ratio with another in indeterminate form, L'Hopital's works.
Okay.
So every time you take a derivative, it's its own function, keep going.
So does that mean 1 plus 1 over x is getting to 1 faster than x is getting to infinity?
So yeah, they kind of, exactly, it's sort of getting to one a little bit faster, and they agree somewhere in the middle. They agree at E. It's a really neat thing if you think about it.
So answer supposed to be like that?
Yes.
Of y?
Well, y was The f of x. So the limit of that is e. Yeah.
Oh, okay.
Cool. I like it. Y was what I called that, and I'm just being lazy. Or maybe. All right. Anything else in homework? Or general ideas? All right. Let's get back into. Let's do an optimization problem. I hate you, clock. And then we desperately have to get into Newton's method. And 4.9, we're going to push off to the next test. Yay!
What was the section you said, 4.6?
Yeah, it's not even on your formula sheet. So on your homework sheet, 4.6. All right. So nobody has any specific questions from 4.7, guys? Guys? All right, let's do one example, and then you guys got to bring it tomorrow. Bring some questions.
Optimization.
Let's see. Well, all right. Let's try this here. All right, guys. So it really doesn't matter how I draw this ellipse. But let's just choose to draw it like this so it's bigger in the x direction. But somebody help me out. How long is this?
Is it x squared over a squared?
So how long is this?
A squared?
It's a. Why? Because what's with the x? A. Remember, that's awesome. Whatever's with the x is what's in the x direction. Whatever's in the y is what's in the y direction. So how long is this? B. That's crazy. It's not a circle because we're assuming A and B are not the same. If A and B were the same, it would be a circle. Alright, and I want to inscribe a rectangle in here. So let me see. So that's the ellipse. Let me draw a fresh ellipse and just draw a representative rectangle. Okay. So I want the largest rectangle that I can fit in that ellipse. Right? So you have a lot of freedom on these problems, and these geometric problems especially have a specific kind of freedom. I can put the coordinate system wherever I want to. So where do you think a good place would be to put the origin? No way. So put this. That's where it is. But I'm gonna go with what you mean. Be right in the center of that thing, right? So have 0, 0 be right in the center of that ellipse. Because it doesn't change the math. If I move my coordinate system, it shouldn't change the math of the situation. So somebody help me out. What do I need to know? So they gave me the fact that the rectangle sits inside of this. Therefore, for example, that point, those vertices of the rectangle have to do what? When you do what with them? So, no. This point here, xy, has to do what? Where is that point xy? It's on the ellipse, therefore it must work in the equation. Let me call it x naught, y naught, just to make it a little less general. Let me stop there for a second. So this is still the same kind of setup. They tell me something. They tell me that I'm working with this ellipse. But what does that directly relate to? Any points that actually, my rectangle, hit the sides of the ellipse. Those points have to actually live there. What do I have to figure out now? What do they ask me? What do they ask me then?
Largest area.
Largest area. So let's designate some stuff here. How do you want to say? Well, see, now the way I would do this is, for example, what is this? How long is that? It's not A, is it? It doesn't go all the way to the end, does it? It's not. I love it. And how long is this? Why not? All right, now you guys kind of with me here so far. All right, so you're picking up what to do when they tell you that something is inscribed in something else. You could approach it this way. Sometimes there's easier ways to do it, but you can always try to do this. I like that. Now, get inside my thought process. If they ask me about the area, I need to know what the side lengths of the rectangle are to write the area formula, right? So I want to write it in terms of something I kind of know that's involved in this problem. So how long is this side of the rectangle? 2x naught. 11. How long is this, of course? 2y naught. So what's the area of the rectangle? 4x naught y naught. 11. Kick ass. I don't know if those little knots are going to mess us up or not. Oh well, let's just keep going. So I want to largest. I want to maximize this bad boy. There's two variables there. We're not in multivariable calculus. This is only single variable calculus. So what do I do?
Implicit.
Say again?
Have one variable relate to another.
Yes, and they do, of course. How do these relate to each other? What do they have to do? X naught, Y naught. What must they do? We said this earlier. They have to work in this equation. So when I plug X naught, Y naught in, it's supposed to work. So what's true about X naught and Y naught? They have to do this. That must be true. So can you solve for one of them?
Yeah.
Totally, right?
So.
And it really doesn't matter because of the symmetry of the problem if I pick the negative or the positive one. So we're just going to pick the positive. You guys understand? I don't know.
1 minus y squared over b squared times a squared equals x squared.
So if I solve for x naught,
yeah.
it'll be 1 minus y naught squared over b squared times a squared, right? So let me just make that square rooted.
Bam.
Ooh, this looks exciting. So what's my area formula now? So again, I'm still doing the same thing I told you. Using what they tell me to help finish out what they ask me.
4 square root.
Yeah, so the area is 4 y naught times the square root of a squared minus y naught squared a squared over b squared. So your variable is what?
Why not?
Why not? I love it.
Why? Why not?
I don't know. Third base. No. All right, and then you do what with this? Because the question is find the maximum of this, and now this I...
So now we take the derivative.
Yes, now take the derivative to find the maximum. So it's just like any word problem. You build your equation that you're working with, and then you attack it with whatever level class you're in. So in this class, we're going to attack it with calculus. Right? So a few of the problems in this section say inscribe it in the circle. The point is on the parabola. That means that the formula of that circle or the parabola or whatever is going to factor into it. Like this equation factored into it because there was a relationship between every x and y. So of course it's a relationship between that specific x and y that's on my rectangles. That's what helped me get the formula together. I got to kill one of these stupid variables. Die. And I do that very subtly. I solve this equation for one of them so I can replace it. So this would you just take the derivative? What would this involve? Product rule primarily. Yeah. So you don't have to have the little knots in there if that's freaking you out. I don't know.
Well, you have to do push too. Oh wait, no, those are constants.
Yeah, this is just like 1/2 or something.
Okay.
Yeah, it's not quite as bad as it could be. Yeah. So you take a derivative, you get your critical numbers, and then you just got to make sure that you pick the one that's the biggest, right? Because you want the maximum. Okay.
So how do you get your A and B values?
No, we don't. We can't. They're given to us as A and B. So our answer is going to be independent of the choice of A and B.
Yeah.
Obviously, they can't be zero, but right.
So how would you write your answer? Would you just make it generally?
Yes, totally.
Oh.
Now they are constants, like you're saying. When you take it rid of A squared, it's 0, right? Because it's a constant. It's just a constant I don't know yet.
Mm-hmm.
So not truly a variable. It's a constant for a given ellipse.
Okay.
So after you find the derivative of that, of the area, you find the critical number?
Then you set it equal to 0, or you look for where it's undefined. You get your critical numbers.
Okay.
And then you have to check to make sure it's something that will actually maximize the area.
Well, okay.
And to tell you honestly, there were functions just like this back in the find the critical number section. So this is not a function you haven't seen before. It's not the prettiest function it could be, but it's a function that they've actually thrown functions like this at you before. All right, so you should be able to take this guy's derivative, set it equal to 0. That's the algebra step. Okay. So do some of those for tomorrow. So we have some questions to really go over. So I want to focus on 4.8 and all the massive amounts of time I have left. And the beautiful thing about section 4.8, the explanation of why it works is not terribly intense. And then the computation behind doing it is not terribly intense. So 4.8 is a nice little, coming down from all the weirdness of what we've gone through. So let's see if you guys agree with me on this.
Kappa.
What's up?
Kappa. But with a horizontal asymptotic. Never mind.
Okay. Oh, you think about this guy?
No, you were saying we're coming down, and I was saying.
Oh, I see. All right. I
was trying to be funny in this one.
I understand. I appreciate the attempt. Okay, so here's the idea. It's almost too simple. And I don't know if anybody's ever thought about these calculators and how they do what they do. They're not just hardwired to know every answer to every possible function. They attack a function as it comes using little algorithms. So this is one that calculators use a modified version of to attack these things. And it's to find roots of equations. So the classic problem would be something like, let me give myself a nice picture to start with. Yeah, that's good. I like this. So there's the root. And I want to find that root by hand. I want to figure out how does the calculator do it, right? We're the humans. We're learning more and more math. Screw you, calculator. I want to know what the hell you're doing. Little magic box of stuff. So now watch. Here's the idea, and then we'll go through the little rigor to get the formula, and then it's just going to be plug and chug city, right? Here's the idea. I take a guess. Now, my guess has to be based off of something. We'll do a few examples, and I'll show you how to get a good guess. Because if your guess is bad, the thing goes to shit pretty quickly. In most situations, it'll go to shit. But let's say if I guess this, I'll say this is my first guess for what the answer is. So remember, we don't have this graph. We just have the function, and I'm making a guess as to what the root is, right? So if I gave you this function and it said, take a guess as to what the root is, we'll talk about how you can kind of figure that out. One quick way is to figure out where is it negative, where is it positive, and the root must be somewhere between. So that would lead to a good guess. Are you guys understanding? So there are several ways to figure out a good guess. How you guys doing? So we don't know this. We have a function we're dealing with. So we pick a guess for what the root is. I would put money on us being wrong. Right? Not because we're dumb, but just because we're human. We're not calculators. Now watch. This is what the algorithm does. It says, okay, here's f of x1. Right? Oh, calculator's laughing at us. That's not 0, dummy. Like, shut up, man. But what we do to make an improved second guess is we use the slope here to construct the tangent line. You can do it, Jeff. And this intercept is our improved second guess.
Oh.
And then what do you think we do?
Then we take the tangent time.
Then we look at the function value. We say there's f of x2. We create the new tangent. And now, of course, this function happens to be one that works really nicely. It's very nice. It's kind of leading us to it. I don't know if you can imagine if I had a root that was near where it's tangent, and I pick the tangent line will say, Oh, shit. So it's not hard to make this fail epically. That's why there's modified versions that calculators use. If the calculator go, that's obviously wrong, let me move your guess a little bit and try again, right? So it's got that built in. But we're looking at the pure base heart of the idea that Newton came up with. Okay, so now that's the idea. Hopefully you guys get the idea. The idea is pretty simple and remarkably powerful. Here's the work behind it. Let's do this first step. So given x1, we find, that's f prime is the slope. We find this, right? So we got the point x, f of x1. We have the slope f prime of x1. What's the equation of the line then? Yeah, y minus y1 equals f prime of x1.
X minus y.
I'm sorry.
X minus.
So just using the point, right? The x piece of the point, the y piece of the point, right? So the same good old y minus y1 equals mx minus x1. Right? Come and save our ass so many times. So
Somebody's getting
that is this purple line, right? The aliens, this is like on signs, right? This is the purple line's equation. Are you with me? This is the purple line's equation. Does that make sense? Because I built it off of that slope and that point. That's the purple line. What point does that purple line go through that's really important to me?
0.
It goes through this point. What point is that? No, come on. Which is 0. So that's the root of that tangent line, which is closer to the root, which I hope, if I'm careful with my guess, is closer to the actual root of the original function. All right, maybe. And of course, the closer my initial guess is to that point, then the more that the tangent line should be close to what the function's doing. That's the whole idea behind linear approximations, right? So that's why a better first guess, the root of the tangent line has to be close to the actual root, because the tangent line will be close to the actual function. Like that, everything's kind of coming together here. It's kind of nice. So now, look what I'm going to do. Look what I'm going to do. I want to figure out what I want to figure out what x2 is in terms of x1, and I can do it now because I know what that line goes through. I can plug that in. Plug that in. So this is y, this is x. So this will be 0 minus f of x1 equals f prime of x1 times what?
0.
No. What's the x piece? x2 minus x1. So I really want you to understand, I built this equation off of that point, this point here, right? But now I'm plugging a specific point into the equation. Why did I do that weirdness? Because I want to get x2 based on x1. Because by hand, given an x1, I want to know what to do to get x2. And then what do you think I'm going to do to get x3? Same damn thing. x4, same damn thing. And then whatever more x's I need, right? So can you solve this for x2? Yes, you can. Yes, you can.
I think it's just 1 divided by f prime of x1.
Yeah, so you would divide this, then you can add x1, right? So it'll be x1 minus f of x1 over f prime of x1. It's a really nice symmetry there going on. So in general, what do you think xn is? Or let's say xn plus 1. What's xn plus 1? What's the next guess? How's it based on the xn? It's in that form. So it's going to be whatever xn was minus f of xn over f prime of xn. Alright, so let's try this with an actual function. There's the word. Let me get a real quick example here. Sure, man. So if I'm given this function, do I got? Okay. Oh, let's make the x cubed. I think that's what it is. And that's a minus 5. Screw it, it doesn't matter. Blah. Now, to get a good guess, what is f of 0?
-5.
It's negative. And what's f of, I don't know, what's going to work here? 3.
27 minus 6 minus 5. So 27
So it's
minus
positive. So somewhere between 0 and 3, there's a root. Are you guys cool with that? Because if it's negative and then it's positive and it's a continuous, it's a polynomial, it's got to go through freaking 0. Right? That sounds like a theorem we talked about before. So, right, like the guy walking up the mountain. So anything between 0 and 3, probably, I don't know what it'd be closer to. So what do you want to pick for a first guess? 2. I like it. So we'll say our first guess is 2. How do I build my second guess? Well, a really good idea. Let me see if I can show this to you real quick. Let's first build what xn plus 1 is. It would be xn minus, let me put this over here. So that's going to be our guess. Minus f of xn. Well, what's f of xn?
2 cubed is 2 to 8 minus...
No. xn. So it'll be xn cubed minus 2xn minus 5. And what's f prime of x?
3x squared minus 2.
So what's f prime of xn?
3xn squared.
Alright, now. Let me show you something really, really nice. So that you don't have to do a lot of work over and over by hand. Freaking time. Bend to my will. It doesn't work, does it? Try it in college. Project's doing 5 minutes. Time! Alright, so if you want to borrow a calculator, I want to show you a really cool way to do what's called iterations. What am I looking for? Use. Because what I want to do, do you guys understand what's going on here? I'm going to get x2 based on x1. And then whatever x2 is, I'm going to get x3 based on x2. So I'd rather have a way for the calculator just to immediately take the last output and put it back in as an input. And then I could just cycle through and get it. So let's see how that works.
Oh, so you build that, and then...
Yes, no, watch. It's kind of nice. Brought to you by Hands-On.
Ideas for life.
Alright, so go ahead and put in... Oh, go ahead and put... No. Let me show you what's going on. Become the right thing. Don't put anything in yet. Sorry. Get away from there. You don't want that. As I'm doing this, I'm forgetting what to do. So here's the beautiful thing. Wherever in the function you see xn, we're actually going to use, in the calculator, we're going to use ans. Because that's temporary memory. It holds the last thing on the screen. So if I run it, it'll have the new guess, and then if I hit enter again, it's going to put that last thing on the screen back in. So it is going to be the output going back in as the new inputs. So let's see how that works. So the first thing you do is to get it started, you hit the number 2. Enter.
2.
Now 2 is in temporary memory, right?
And the answer.
So now if I just put that whole thing in, answer, what? Uh-oh. Is it dead? No. Oh, you just, all right. You're over. I understand. So wherever I see an xn, I'm going to put ans. Minus ans cubed, right? Minus 2 ans. I realize that it sounds like anus, but hopefully I was just flashback. I'm like, that's what I'd be saying out in the crowd right now. Is he saying anus? You guys see what I'm doing? I'm doing this, which came from f and f prime. I'm doing this equation, but everywhere it says xn, I'm putting No, I'm never going to be able to say that again.
Anus?
What? So, what am I doing with my anus? No, just, I'm not sure how to handle that question.
Recording.
Huh? Oh, yeah, sure. Yeah. Hey, Dean. Alright. Now watch. So, what really sucks, now if you don't like what I'm about to do, you can do it by hand every time. You can put a 2 in, and then whatever your answer is, you can put that in, and then whatever your answer is, you can put that in. But dear God, we're past that, right? That's Math 90 shit. So hit enter. That would be my next guess. Then you hit enter. So if you hit enter, it's going to redo what it did. If you just keep hitting enter, it's going to refine it. Now, real quick, just to, you guys, so every time I hit enter, it reran what I had in there, but now the second time I hit enter, it had 2.1 in for ANS. And then it had 2.0945 in for ANS. Now, real quick, if I graph this, you can see what the actual answer is, right? You can let the calculator run its own modified Newton, blah, blah, blah. So if I put x cubed, let's see if the answer was right. What is it, minus 2x minus 5?
Yeah. Newton's method, right?
Newton's method, yeah. Alright, there's the root there, right?
There it is.
So if I calculate 0, and now you understand why it asks for bounds. That's part of the modification. So it knows if it gets outside of there that it's gone too far. And there's the 2.09. Look at that. That looks very familiar. So we can do, well, when I say by hand, we're still using calculator, but we can do by hand what the calculator is doing, programmed to do. So scheisse. I got like several things here for you. You want 2 things here real quick.
That was so sick.
How would you do this generally? ANS minus.
So one of these is the practice test. I'll have the answer to you next time. And the other one is the handout about Newton's method.
Let's say your guess was 3, but the ANS 3.
Oh no, you put it into the temporary memory. So the first thing you do is you put an answer into temporary memory. So you say 2, enter. So 2 is in the temporary memory. Then you create your function ANS minus ANS cubed minus 2 ANS. And then when you hit enter again, then the temporary memory is
The temporary memory becomes that last output.
So let's say it was 4. I would put in 4, I would answer, and then I would build the exact same thing, or what would you do?
Yeah, so then you build the actual function you want. So if you did ANS minus ANS,
Oh, then it would be ANS to the third minus 2
ANS minus 1. Exactly.
Okay.
See, if you did ANS minus ANS right now,
Yeah.
it's 0. If you put it in 0 again, it's 0 again. But if you change the input by, then you do ANS.
One of them will be in the other one.
Plus ANS. 10, 20, 40, 80. Because it takes the less. Isn't that sick?
Okay, that makes more sense now. I was wondering where the coefficients of powers were.
Oh, gotcha.
But now
You guys, really? You're so mean. Alright.
That is so sick.
You're still here. Watch this real quick.
Oh.